The next type of RCC water tanks is underground tanks. So in this lecture we will be studying the rectangular underground water tanks. So this was the detailed classification of RCC tanks, and we have covered this part, that is tanks resting on ground. Now we are moving to the next type of tank, that is underground tank, in which I will be covering rectangular tank first. So as in the previous case of tanks resting on ground, the underground tanks are also of two types, rectangular or circular, and rectangulars are of two types, L by B less than 2 and L by B greater than 2, and circular tanks are with flexible base or rigid base. So the design of walls will be similar as done in the previous case of tanks resting on ground, but with a minor difference which I will be explaining you in the coming slides. So this is underground tank. The underground tanks are located below the ground surface. The top slab can be buried below or can be on exactly the ground surface. It can depend on different situations. So the parts of underground tank are the long wall of tank, short walls of tank, the base slab or bottom slab, and the top slab or roof cover. Now, unlike in the previous case of tanks resting on ground, where we were not bothered about the slab or the cover of the roof because there were no loads acting on the top of the tank on resting on ground. But as you know that the tank is located below the ground surface, therefore at this is the ground surface, then some loads may occur on this tank. So a top slab has to be designed for the vertical gravity loads, which can be anything which is either live load or dead load of any type of structure or any type of movement possible on the ground surface. So we will be designing 4 components here. Long walls and short walls are designed in the same way as in the previous case, with depending on whether it is rectangular tank or circular tank. So first we will do tanks, rectangular underground tanks with L by B greater than or equal to 2. I will be explaining you only this type of tank because you have already done L by B less than 2 in the previous case, and I will be explaining L by B greater than 2 here, and the design of underground tank with L by B less than 2 will be exactly same as done in the previous case, with the additions which I will be explaining you in this slide. So first of all, we must know what are the loads acting on underground tank. Now this is the major difference between tanks resting on ground and underground tanks, is that this is below ground surface, therefore this is the earth fill present around the tanks. So there are 2 loads which act on a particular wall. If we consider this wall, then due to water an inside load will be acting on the inner face of this wall, and due to this earth pressure an outside load will be acting. So the loads acting on tank walls are 2, that is water pressure due to water present inside the tank, and earth pressure due to the earth field present around the wall outside the tank wall. So this is the phenomena of load. So how do we consider these 2 loads together? I will be explaining you in the coming slides. Now we move on to base slab. In the previous case of tanks resting on ground, we were designing base slab for a minimum amount of reinforcement and minimum thickness, but we cannot do the same here. What is the reason for that? In the underground tank, as you can see, whole of the tank is buried inside the soil, so it is totally surrounded by the soil. So the bottom slab or the base slab of the tank is also acted upon by the soil pressure from below, and its tendency will be to uplift the tank. So if this is the base slab, and this is the upward soil pressure acting on the soil on the bottom slab, so its tendency will be to uplift the bottom slab, and there will, due to the presence of soil around this tank, there some downward earth pressure will also be acting. So we have to consider all these, and along with that other loads are also acting, from the earth pressure here, the water pressure here, the vertical loads, etc. So we have to design the bottom slab due to these loads, that is the upward soil pressure from soil supporting the slab shown here, the downward weight of water shown here, the downward weight of walls and roof slab. So all the vertical load of the walls and the top slab will also act on the base slab. So these are the various types of loads acting on your base slab. In detail I'll be explaining you but how these loads are calculated and how do we analyze due to these loads. And the last component of underground tank is the roof slab. As roof slab is buried under the soil, so as I explained earlier, it can also be subjected to various loads. So if this is a tank, underground tank, and this is the roof slab and this is the ground surface, if anyone is moving above this tank, or if there is any structure present here, so the dead load and live load from that may act on this particular tank. So we have to consider those gravity loads. So this top slab is designed to carry the gravity loads and acting on the slab. Now I'll be explaining you how do we design tank walls. So the long walls and short walls are designed in a similar way as we studied in the previous case, but here there is one very important difference. As I told you, the tank wall, if this is a tank wall, it is subjected to two loads. One is water pressure and one is the outside face is subjected to the earth pressure. So we have to consider both these loads. What we do is that we consider both these loads acting on the wall separately. That is, first we assume that the tank wall is subjected to only earth pressure. This is the first case. And in the second case we assumed that there is no earth pressure and the tank wall is subjected to only water pressure from inside. So we design and analyze for this load, that is earth pressure. We design and analyze due to this load, that is the water pressure, and then after getting the analysis and design of both these, we combine both these to get the final reinforcement. So analysis of two conditions for calculating the moments and forces on tank walls is required. As for reinforcement calculation, we require the forces and moments acting on the different components. So what we do is we consider two cases. First case, in which tank is considered to be empty, that is there is no water inside. So if there is no water inside, hence there will be no water pressure, and active earth pressure acting only on the walls. So this is the first case, when there is no PW, that is no water pressure, but there is some active earth pressure due to the soil present outside the wall. The second case is when the tank is full. Tank is full means there is water present inside the whole height of the tank wall, and there is no earth fill, means there is no lateral earth pressure present from outside. Hence we consider the first case for design of wall, then we consider this second case separately for calculation of moments and forces. Then due to these moments and forces, we calculate the reinforcements for both the cases, and then we combine both these together. So it will be more clear to you when we look at the question. So what is the case 1? What will be the case 1 when tank is empty and active earth pressure is acting? So we consider only the earth pressure. So it is almost similar like that of retaining wall, with the difference that the outer face of wall is subjected to this earth fill. Okay, so this is the tank and this is inner face of tank, this is the whole tank. So here there is no water and only earth pressure is acting. So there can be two cases, as we have explained, we have done in the previous questions of retaining walls also. First, dry soil. When the soil is dry, then the maximum earth pressure will be at the bottom of the wall, which will be Ka gamma into H, where gamma will be the density of the dry soil. And in the second case, that is active earth pressure in wall for saturated soil. If the soil is saturated here, then the earth pressure diagram will be like this, that the saturated earth pressure will be Ka gamma dash, that is gamma submerged into height, and the pore water pressure will be gamma W into H. So I have already explained to you many times how do we get this diagram. So the PA will be maximum at the bottom of the tank wall, which will be Ka gamma dash H plus gamma W into H. Now in this case, what will happen, this is the outer face of wall and the little earth pressure is acting in this direction, and the water tank wall, if it behaves like a cantilever, obviously that will depend on the type of tank we have, so it will undergo tension like this. If this is a cantilever, so the reinforcement will be provided in this case here. Now the second case, when tank is full and no backfill, this is the same case which we are doing in the previous case, that is PW is equal to gamma WH. The water pressure is maximum at the base and there is no earth pressure from outside. So we analyze it in the same way as we did in the previous case, depending on whether it is a rectangular tank with L by B less than 2 or greater than 2, or circular tank with with a rigid base or flexible base. Now look at these two diagrams here provided, which I have drawn below. For case A, this is the load diagram, which is the earth pressure diagram, so tension is on this face, and this is for case B, where this is the water pressure, so the tension will be on the inner face if it behaves like a cantilever. So what we do is that first we design, for example, if we are considering rectangular tanks with L by B greater than 2, then we design the long walls first with case A for this load only, that is earth pressure, and then we design the same long walls for case B, and then we combine both these to get the final reinforcement. Then we design the short wall with first case A and then case B. If we have circular tanks with rigid base, for example, then we design the tank wall for rigid base with only earth pressure, that is case A, and second case for water pressure only, that is case B, and then we combine the reinforcement. So this is how it is done. It is a bit lengthy because we have further broken down into many other cases. Now next is the design of roof slab. So roof slab design is very simple, which you have done earlier. So roof slab is basically a slab, horizontal slab, which is acted upon by vertical forces, downward forces, which are the dead load and live load. So we design it in the same way as normal slabs are done, that is either one-way slab or two-way slab. So we will have the L and B value of the tank. So for this slab we calculate the L by B ratio and we determine whether it is one-way or two-way slab. One-way slab is the one where L by B is greater than 2 and L by B is less than 2 for two-way slab. Then we calculate the moments due to these loads, live loads and dead loads, and we calculate the main reinforcements and distribution reinforcements in the top slab. Now next is the base slab. So the base slab is subjected to, as I explained previously, the upward soil pressure which is acting on the soil beneath, and it is also and due to this upward soil pressure, the tendency of the soil will be to uplift this tank or this base slab in the upward direction. It will try to push the slab in upward direction. If that happens, then the whole tank may fail and it may displace from its position. So to avoid that, for the stability of tank, what we have to do is to counteract this. The tank will not move or will not uplift when the upward force is balanced by some downward force. If both forces are balancing each other, then the upliftment will not take place. So we should have more and more downward force so that this particular force is counteracted. So to increase the weight of the soil, weight of this or the downward load, what we do is we project the base slab along outside the walls. Like if this is a rectangular tank, then the base slab is not provided just below the walls, but it is projected below the walls in all the directions, like I have shown you in the previous diagram. Let us look here. Here you can see the bottom slab or base slab is projected outside this long wall and this short wall and this long wall and this short wall. So the main purpose of this particular projection is that due to this projection, the soil will rest on this slab, and the weight of this soil will add to the downward force. So our purpose is to increase downward force so that it can counterbalance the upward force. So this weight of this downward weight of the soil in projected portion will help us in that. Now after we have calculated all these forces, okay, apart from these we have some other forces, like the weight of tank walls will also act in the downward direction. The weight of long wall, short walls, and weight of roof slab will all act in the downward direction on the base slab. So we calculate all these forces and we analyze all this diagram. This is the loading diagram now. We analyze this loading diagram and we calculate the maximum moments and forces due to these loads. And after that, when we have calculated the moments, we will find the reinforcements. So this is how the tanks are designed. Now we will continue with the design problem. So now we will start with the design problem of a rectangular underground tank. So here you can see the question is to design a rectangular underground tank of size 10 meter by 4 meter by 4 meter, which is the density of the soil around the underground tank is taken to be 16 kilonewton per meter cube, and it is a saturated density. This means the soil is saturated. The angle of internal friction is given and the live load acting on the top slab is also given. So we have to design this tank. So I have taken, as you can see, the L is 10 and B is 4. So L by B ratio is coming out to be greater than 2. 10 by 4 is 2.5. So I have taken this question here because in the previous video lecture I had not explained to you how the tank walls are designed when rectangular tank has L by B greater than 2. So I am explaining that in this as a part of this question. So whatever I tell you in this particular lecture, in the same way the rectangular tanks with L by B greater than 2 resting on ground will also be designed, with the difference that here we are taking soil pressure and in the tanks resting on ground we will not be taking the soil pressure. I hope you understand this part. Now let us begin with the design. So first step is calculation of design constants. Next step is the determination of what is the type of tank. So as I told you, L by B is greater than 2.5. Therefore this is we have to design it as a rectangular tank with L by B greater than equal to 2. Now we also know that soil condition of underground soil is saturated, so we calculate gamma dash here only, submerged unit weight, which we will be using in the coming calculations. Now as L by B is greater than 2, so in the previous video lecture I explained to you that how the tank walls will behave when L by B is greater than 2. When L by B is greater than 2, then the long wall and short wall will behave differently. The long wall will behave like a cantilever up to full height, and the short wall will behave like a cantilever up to height small h, and continuous frame action will be subjected on the upper part. So and in the L by B, if the same question was for L by B less than 2, then here long wall and short walls will behave similarly. That is, on the bottom portion cantilever action, and then on the top portion continuous frame action. So we will be doing this like for this. So next is, now as this is an underground water tank, so we will have to consider two load cases. That is, first when only earth pressure is acting on the tank wall, and another when only the uh, water pressure is acting on the tank wall as well as the base slab. Okay, so we will do the design separately for both these cases for each component. So first of all, I will do the design of long walls, because long walls and short walls are behaving differently, hence we cannot do the design of walls together here. So in first step I will design long wall, then short wall. If in this question L by B would have been less than 2, then you can design long wall and short wall simultaneously, because the behavior is totally same, just the values will be different, calculations will be slightly different because of the different height lengths of the wall. So I will first design long wall. So long wall behaves like a cantilever up to full height for two loads. First is, if this is a long wall of the tank, so if soil is filled in this portion, this is the long wall, then there will be earth pressure acting from this direction, and the water pressure will also exert pressure on the inside. So we will consider both these cases individually and calculate the forces. So first case I am taking to be the design of long walls when the tank is empty and active earth pressure is acting on the walls. So only we will consider earth pressure, forget about the water pressure for now. So long wall behaves like a cantilever up to capital H height with force. This is the lateral earth force which is acting, as this is a saturated soil as given in the question. So the lateral earth force diagram will be like this. So the total maximum earth pressure will be at the base of the wall, and it will be Ka gamma dash H plus gamma WH. So first of all we calculate Ka. As this is active earth pressure, Ka will be 1 minus sin pi upon 1 plus sin pi. So we calculate Ka and we put it here, and gamma dash we have already calculated. This is 16 minus 10, that is gamma saturated minus gamma W. So we put all these values here to get Pa is equal to 48 kilonewton per meter square, and the force due to this earth pressure will be the area of whole of this triangle, which is half this Pa into height, capital H. So we get the lateral earth force to be 96 kilonewton and earth pressure to be 48 kilonewton per meter square at the bottom. This will act as at a height of H by 3 from the bottom of the wall. So now as this is as it is a long wall which is undergoing cantilever action up to full height. So what will happen? This is the wall and load is acting from outside, and this is showing cantilever behavior. So it will bend like this, which is opposite to that of the circular tank with rigid base acting resting on the ground, and also retaining walls also. So cantilever bending moment due to this lateral earth force will be Pa into H by 3, maximum at the bottom. We get it to be 128 kilonewton meter. Now we calculate the thickness required for wall, which will be under root of m moment of cantilever in the long wall upon Rb. So I am getting it as 292. It is the effective depth. So I adopt a total thickness of 350 mm with 40 mm cover. So effective depth provided is 310 mm. So it is more than 292, hence okay. You can also increase this up to 400, any value above it, with the condition that it should be more than 292. Now the vertical reinforcement is provided in the long wall due to this cantilever action, so we calculate this reinforcement and it is coming out to be 20 mm dia bars at 80 mm center to center on the outer face of long wall, because as I explained to you, this is the tension face now, and these bars can be curtailed towards top as the bending moment is reducing towards top. So you can curtail also, as I have explained to you, that at different heights you can curtail the bars according to your choice. So this was the vertical reinforcement. Now there will be let me make this diagram here. This is the lateral earth force diagram. Now due to this lateral earth force diagram, there will be some compression also acting on the thickness along the wall, because its direction is like this, so there will be compressive force. In the previous cases, whenever we studied the water pressure, there was tension because it was acting on this direction, so this was leading to this pull. Now this as the earth pressure is acting on the outer face, this earth pressure will lead to compressive force. So we use the term direct compression here, not direct tension, because of the position of load on the outer face. So the direct compression in long wall will be maximum at a height of small h from the bottom, as we have already studied earlier. So it will be 1 meter, 1 h by 4 or 1 meter. So now we first of all calculate the pressure, earth pressure at this particular point. So what will be the earth pressure here? Ka into gamma dash into this height is h minus h, plus gamma w into h minus h. So I hope you understand. Earlier we had calculated the pressure here, which was maximum. Now we are calculating it at height this, because we assume it that the direct compression or direct tension is maximum at height h minus h. So we get this value to be 36 kilonewton per meter square, sorry. So now the direct compression will be PA into B by 2. So if you remember, it is exactly same. I will remind you when we did the tanks question. So rectangular tanks question with L by 2, we had the value for direct tension as gamma h minus h into B by 2 in the long wall. So here gamma h minus h was PW. This gamma h minus h was PW. Now we have substituted this PW with PA, because this is the case of active earth pressure, and this will be B by 2. So I hope you understand it is same as we did earlier. And another difference is here we were considering tension, now we are considering compression due to this direction of loading of your earth pressure. So the direct compression will be 72 kilonewton. So the horizontal reinforcement due to this earth pressure will be provided due to this direct compression, which will come out to be which is coming out to be 554 mm square C by sigma st. Now minimum reinforcement is 0.35% of cross sectional area, as you know. So 554 is less than 1222.5, hence we provide reinforcement equal to minimum. As this is the minimum reinforcement, we distribute it on both faces of wall, and so we provide 10 mm dia bars at 120 mm center to center on both faces of long wall. Now this was about the case A. So what we did in this case, we considered only one load, that is the active earth pressure, and we designed the long wall, that is the vertical reinforcement in long wall and the horizontal reinforcement in long wall. Now we will design it with short wall. Okay, sorry, with case B. Now I will make one change here. Do not provide it on both faces, okay, because I will explain why not both faces. Provide this reinforcement on only the inside inner face of wall, because sorry, the outside face of wall, okay. Don't provide it on both faces right now. So now we will design the long wall for case B, that is tank is full, hence water pressure, there will be value of water pressure and there will be no active earth pressure. So this is same as we did previously. So maximum water pressure at base will be gamma W into H, so we are getting it at 40. So cantilever moment due to this pressure will be half into gamma W H into capital H, because the cantilever action is acting on whole of the wall, and the cantilever moment will be force into H by 3. So we get cantilever moment this. We provide vertical reinforcement, which is coming out to be this, and we are providing it on the inner face because, as I have explained to you earlier also. Now there will be direct tension due to the inside water pressure. So here we are writing T, and in the case A we were writing C. So this is coming out to be 60 kilonewton. Here T is PW into B by 2, and in the case A, C was PA into B by 2. So we provide horizontal reinforcement and we provide it on this is provided on the inner face. So I hope you know why I had changed that in the previous, because here also we are writing both faces and there also we are writing both faces, so one has to be on the inner and one has to be on the outer. So this is the and by chance we are getting both these reinforcements same, because both are minimum reinforcement, so there is not much different, but still while writing you must take it into consideration. So this is the summary of reinforcement in long wall. So always summarize your reinforcements for your clarity, that will be beneficial for you. So for case A we got vertical reinforcement as 20 mm at 80 center to center, and for case B we got as this was provided on outer force and this was provided on the inner face. Now as I explained to you, as the moment reduces towards top, you can curtail the reinforcement. So we have curtailed it 2 times, so the final reinforcement we get is 20 mm. First curtailment we did at 1.5, then the next curtailment at 2 meter height. Okay, so we get 20 mm dia bars at 80 mm center to center at 1.5 meter high, which is the bottom portion where movements will be maximum. Then we curtail some bars, so there will be double reinforcement for this height from 1.5 to 2 meter. Then we again curtail the reinforcement, so you will have this reinforcement. So I will show you how this is done. If this is the wall, first reinforcement we are providing up to 1.5 meter height only. Okay, now next reinforcement we are providing at a height of 2 meter. This is 2 meter, and next reinforcement we are providing up to full height, that is 4 meter. So we get such reinforcement here. So we repeat this reinforcement like this. So as you can say, in the 1.5 meter meter height, you get the reinforcement spacing at quite less, which is 80. In 1.5 to 2 we get, this is 1.5 to 2, so we get double, that is 80, double of 80, that is 160, and in the upper portion we get only this much reinforcement, which is 320. So I hope you get this point. Same thing is done on the inner face, that is for case B of water pressure. So we have done curtailment 2 times, so we get 3 types of reinforcements. You can curtail only once also, it is up to you. And the horizontal reinforcement for case A as well as case B was this much. So what we do is, we are now getting the reinforcements on outer face vertical here, and on the inner face vertical reinforcement this, and the horizontal reinforcement on outer face and on inner face. So I hope now you can visualize what will happen. In the outer face, this is the plan of your long wall. This is the outer face horizontal reinforcement shown in red line. This, which is 10 mm dia bars at 120. In inner face also we have the same quantity of bars, that is 10 mm at 120, and the main reinforcement is the vertical reinforcement. On the outer face we have 20 mm dia bar at 80. So we have three types of reinforcement here: 80 cent spacing, 160 spacing and 320 spacing. And in the inner face we have 100 spacing, I've written it here, 100 spacing, then 200 spacing, and then 400. 100 spacing, 200 spacing and 400 spacing. So this is the plan. The cross section at, if I cut a section 1 here, so cross section will look like, if this is the inner face, then the vertical reinforcement is shown in three heights, that is 1.5 meter, 1.5 to 2 meter and 2 to 4 meter. So this reinforcement on the inner face is at spacing 100, this reinforcement as 200 and this as 400. And on the outer face this is 320 spacing, 160 spacing and 80 spacing. And the horizontal reinforcements are shown here in red dots, 10 mm dia bars at 120 on inner as well as outer face. So this is the plan of your long wall, this is the cross section, and this is the side elevation of your long wall showing the three heights of reinforcements. I have prepared here only the outer face, so I am getting the reinforcements at 80, 160 and 320. Same will be for the inner face also, with the spacing as 100, 200 and 400. So I hope the design is clear to you. So at the end of the design of long wall you can summarize the reinforcement and show it like this, so that you have clarity while drawing the detailing as I did here. So this was the design of long walls of the underground rectangular tanks.